Hello, welcome to our semiconductor education program. This is Vincent Chang. Today we are going to start a new series on the subject of multivibrator. So I'm going to teach you three types of multivibrators. So number one, bistable multivibrator. And next one will be the astable multivibrator. The last one will be the monostable multivibrator. So again, the bistable, astable, and then monostable. So let's start with the first one, the bistable multivibrators. So I'm going to teach you about the fundamental bistable, the concept, bistable multivibrators, and I'm going to teach you 3 lectures around this topic. And bistable multivibrator, also known as Schmitt trigger, Schmitt triggers. The key concept explained. Let's start with the positive feedback loop. Again, it's the positive feedback loop. So watch carefully. The connection between the output terminal and one of the input terminal, which is the positive input terminal, the non-inverting input terminal of the op-amp. Right? So it's not negative feedback loop. It's a positive feedback loop. And then let's think about this. So in a negative feedback loop, so one of the important characteristics of the negative feedback is what we call virtual short. In other words, the voltage between the 2 input terminals are the same. So let's assume when you turn on the power supply of the op-amp, and then the initial voltage of the positive terminal is equal to the negative terminal, which is ground. So let's start with this initial condition. V positive equals V negative equals 0 volt. All right? So let's assume this is a reasonable initial condition. And then what? Then when we turn on the power supply, it's inevitably creating some sort of a disturbance, a noise, an unwanted electrical signal. And then let's pay attention to the positive terminal, the green node. Assuming the disturbance is an unwanted electrical signal going toward the positive direction. So now, what you see on the slide is the definition of. Let me clarify this. All right. So beta is the feedback factor. Remember, we talked about the feedback loop. So the feedback factor is defined as the R2 plus R1, put it in the denominator, and then what's the numerator? The R1. So beta is the feedback factor. And then I just talked about, let's assuming a positive disturbance, a positive spike is present at the positive input terminal, the non-inverting terminal. Then what? Then the operational op-amp, the op-amp, the one of the main objective of the op-amp is to what? Is to sense a differential signal between the 2 input terminals, right? And then what? Then because when you have a positive differential, then the operational amplifier is going to amplify. It's going to sense the very small, even it's the very small, positive differential, and then will be amplified by a huge gain, the open loop gain A. Then creating a sort of amplified signal at the output of the op-amp, right? So you can just imagine, picture this. The height of the output spike divided by the height of the input spike is actually the open loop gain, the A. So the arrow with an A means the multiplication factor. And then what? We just talked about the beta. So if you have the 1 unit at the output, so how much change will show up at the positive input terminal through the feedback network? So needs to times what? Times the beta. So needs times the beta. So the height, the electrical magnitude of the signal 2 times the beta, which is less than 1, all right? So R1 divided by R1 plus R2. So times beta will be the 3 and show up at the input terminal, the positive input terminal of the op-amp. So what's the ratio between 3 and the 1? What's the ratio between the amplitude of 3 and the amplitude of 1? This is what we call the loop gain, right? The loop gain. You times A and go back times the beta. So it's reasonable to assume the loop gain is greater than 1, right? So then this is why the magnitude of the 3 is larger than the magnitude of 1. And then the 3 cannot be raised. So because the op-amp is still working, then times the A again and goes to 4. And 4 comes back times beta goes to 5. And 5 should be greater than 3. The magnitude of the signal 5 is higher than the magnitude of the signal 3. Why? Because we just assume the loop gain is greater than 1. And then the 5 yet again times A goes to 6. So going to this kind of the positive feedback, the process, then what's the final voltage of the output voltage? In this case, the saturation voltage, right? The saturation, so output voltage, then it's going to be limited by the positive saturation voltage of the op-amp. Let me give you a physical analogy of this. So the positive feedback loop on your left-hand side is kind of similar, can be analogous to a hill. So imagine you put a ball on the top of the hill, which corresponding is associated with the virtual short. The two terminal voltage are the same. V positive equals V negative. And then can you place the ball on the top of the hill? You can't. Why? Because there's going to be any physical imbalance, any physical a little bit disturbance will cause the ball go to one way or the other. So think about this. What's the analogy of the ball moving toward the right? It's the V positive can be analogous, can be explained as the V positive is greater than V negative, right? And then what? Then the ball will go to like this, right? It's gonna initiate a positive feedback process, right? And in the analogy, the ball will go to the one side of the hill and then sit there, stuck there. So this is, which is corresponding to the output of the op-amp reaches a positive saturation voltage, which is the V capital M. So what about the initial? So in other words, let's do the analogy together. This is the takeaway. So for the positive feedback loop, we have almost come to the end of this lecture. Let me give you a sum up. So when you see the positive feedback loop, especially for the beginner, excuse me, especially for the beginner, it's a little bit difficult to understand this, right? So I strongly recommend you use this analogy. When you see the positive feedback loop, so when V positive is higher than V negative, then what? Then you will initiate under the assumption of the loop gain that loop gain is greater than 1, then you will initiate the positive feedback. The regenerative process will be activated, and then cause the output voltage reaches the positive saturation voltage, just as analogy tells you. The physical analogy tells you the V positive is higher than the V negative. The little bit tendency and a move toward the right, then you can never go back. You will reach the one side of the hill. So what about the other side? So the other side is you can put the analogy of the V positive is less than V negative. V negative is higher than V positive. Then what? The ball will go to the other side of the hill, which is associated with the negative saturation voltage. Look at your left-hand side of the slide. If the initial quantity, if this happened, if V that positive is less than V negative, then what? Then again, the regenerative process will be activated and forcing the output of the op amp reaches the negative saturation voltage. Once this saturation voltage is reached, then the system is stable. So how many stable states does this circuit, the positive feedback circuit, provides? 2, right? So depending on when you turn on the supply, depending on the comparison between the two input voltage. If the V positive is greater than V negative, then positive saturation output will be reached, which is the one stable state. But on the other hand, if the V negative is higher than V positive, then the similar regenerative process will be activated and forcing the output of the op amp reaches the negative saturation voltage, which is associated with the second stable state. So this circuit provides the two stable state. It's called a bistable circuit. So in the next lecture, I'm going to teach you 2 types of the bistable multivibrator. All right? And then the first one is the inverting bistable multivibrator, inverting Schmitt trigger. The second one is non-inverting bistable multivibrator, or non-inverting Schmitt trigger. So see you in the next lecture. Thanks for watching.